So, we're going to source, and I think, I can't remember if we've done chapter 2 or not. Let's have a look. I'm pretty sure we finished chapter 2. We'll have a little check. We'll have a little looky. Let me have a look if there's a font. Is that maybe a little bit bigger? I'll do another one. I'll do another 2. I'm pushing the boat out. Yeah, go on. 2, that's good. So look how far we'd got. So we kind of, yeah, like I said, if you check out the YouTube channel, it's got all the other, I think they're still up on here, but it's got everything else, so like that you can follow along. I think this is as far as we got. I think it's like task 7 or 8. Oh, and then when we did this, it was cool because people on chat were joining in, and we were trying to get, everyone was trying to get their own version of what they'd written, so that was interesting. So that's for take even, and the idea was you give it a list of arrays and then it takes the even, but not by number. It just literally does, is, you know, the first one would be like odd, even, odd, even, odd. Yeah, so this one would take even, and then we like abstracted it out so we could have something that can do both, and depending on what value you give it, it'd be even or not even. There. Magic. That was good fun. So yeah, I mean, if you're following this along and you do it on your own, it's probably not going to take you anywhere near as long as it's taken me. But it's just I'm really going thoroughly in and sort of experimenting out and showing loads of little different techniques that are really handy when you're starting off. One of them being type holes. That's always really important. It's basically, hold on. It's something that you can use a compiler, and if you've got something like Haskell language server, I mean, even if you have the compiler showing you errors, whatever way you decide to do it, you can do something like, so if I do well, definitely don't do it like that. Let me just go back. I like it how it does. Here we go. Yeah, so if we go like this, okay, and then it should come up with some errors, yeah, which it has. Let me just reload this quickly. I don't know why it's got 11 though. I mean, surely it's just 1. It went from nothing to 11. Okay, fair enough. And yeah, I think that's an error. It says 11, but clearly look, there's just 1. But anyway, so it gives you found a hole. Oh, thanks for the follow, Peter Storm. Oh, someone with like a semi-normal name. I like it. Not saying semi-normal, but I have to like get crazy names, like you know, like with numbers and things. I'm just like, yeah, don't know. Anyway, back to this. Yeah, so what it shows you, multiple things. First, it tells you what type it's expecting. I know that might not be too descriptive, you know, it's just a list of A, but that's good indication, better than nothing, essentially. And then it shows you what's available in scope. So that's really good. So it tells you that the value there, A, is actually of the type A. I mean, you'll see it. We use it extensively, and you'll see it. And then it gives you like, you know, saying that you could potentially fit these in there. It's probably going to find it a little bit hard, but if we get something that's like a little bit more I guess with more bits and pieces in there, you know, it gives you better predictions. But it's really good because then what happen, it's almost like, I guess you could say it's like TDD in a way. Not really, but sort of. But ideally, the compiler is your friend. That's the idea. Because I spent a good year or two just going, oh, fucking compiler, what are you doing? What do you mean? You know, like just getting angry because it kept telling me I was wrong. But instead, if you use it in this way where you use type holes, then you're kind of like just saying, hey, compiler, my friend, can you sort of advise me what's around me and what values they are? And then if you install also Haskell language server, you get extra bits like, let's have a look. Here we go. You can get here, so you get some documentations on what values are what. So let's have a little look. Duplicate, for example. No, that's just gonna. Oh no, there is a no. Is that our function? Yeah. Okay. Oh, we made our own function duplicate, but there is a one on yeah, it's one that's part. So it just, you see, it shows you the type. So it expects oh, hi Nicholas. So does it also find stuff from quantified imports? Like if I had an import qualified data, yep, it'll find, yeah, literally. I mean, all whatever's been imported. We haven't got anything. I think we just got data.list. So let's see if there's something down here. Is there anything? I guess there's going to be a map somewhere, isn't there? It's got to be. Map. Where's our map? No, we created our own map. Concat Map. Here we go. That'll do. Cool. So if you look, Concat Map, and it gives you all the types. So yeah. So it's like a T of a blah 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 blah. And then you can then link. You can click this documentation or source, and it takes you somewhere. Except mine isn't right now, but normally it should. Wink. But yeah, it does that, and it does way more also. I mean, you can start doing. Let's see. Here we go. Look, I'll show you. I've got a type hole here. It's found a hole of T, and then this is the stuff it's saying to me at the very bottom what it can be. So we can replace it with index or blah 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 blah, or attempt to fill the hole. Index is telling me. So yeah, it's pretty clever. And from that also, if you're bringing in things that aren't imported, so it will look, you know, all over. So say, I don't know, you use something on base like data.string or something like that, and you haven't actually imported it, then it'll give you the option that if you want to. Oh, thanks for the. Oh, what's this? Raid. Hey, how's it going, Vlad? What happened? I couldn't handle the maths. I've got to watch the ones before. If you haven't, follow Vlad, because he does like loads of different types of functional programming. He does, yeah, from pure script to gotta run, baby. See you later. I'll plug you myself. Don't worry. Yeah. So the idea is he does all sorts, and he streams quite a lot. And yeah, what was he doing? He was just well, today I was just watching before I came on here. He was doing like some maths stuff, and my brain was just going, and because I missed either one or two of the previous streams, and I just didn't know what was going on. If you can't tell, I'm definitely not a mathematician. Don't have a PhD, so that's probably, you know, I'm abnormal for the Haskell community, because I guess you get surrounded by that. So yeah, so it's insane. From what we had only like a year ago, I just used Vim and GHCID. Yep, when I started. Exactly. Same here. Literally, because it was GHCIDE and then Haskell something HIE, and they just combined forces. So I think they were kind of, I can't remember if they're sort of tit for tat, I can't remember, but they ended up joining forces. And from now, it's just like, yeah, it's way better. It's just, yeah, it's just so much more intuitive to use things. It makes nicer, because PureScript was very similar. Well, it is, sorry, at the moment. It's got, I don't think it does a sort of the docs thing. But whatever you used before, it'd also be sort of quite slow, like, you know, for it to build and things like that. There is a slight bug at the moment where sometimes it won't pick up that I've made a change. So I have to like do this where I sort of restart the server. And you can see at the very bottom of the screen it says Lisp restarting server. But I think if you use it with VS Code, it's just wow. Yeah. There you go. How's it going? Yeah, it is just what is. I'm gonna hover over that emoji. What is it? It's just PogChamp. Okay, well that's a Twitch thing, but it looks like something going wow. Yeah, so definitely use it. It's good. And even, yeah, so if you use it, well, I did link it, but I think the chat doesn't. That's the thing with Twitch. The chat disappears if you've not been on. You don't get to see what was on before. I think I did put it in the description, but I'll put it in just in case someone's not seeing. Yeah, I'm good. I've just I don't know, I just wanted something to do, I guess. I'm still waiting on responses from people that don't like to respond when it comes to jobs. So I'm just sitting here sort of, I guess, twiddling my thumbs. And then, yeah, I was going to say, I don't know if you missed it, but I was going to work on this. But then I started to build the compiler. Sorry, started to build a repo, and then all sorts of errors happened. So I'm going to go back onto this for today. But I think if I just get it built tonight, I'll probably either tomorrow or the day after I'll do the property based testing, because this will use yeah, I know, what a shitter. This will do after doing the monad transformers, we were sort of looking at potentially what to do next, and then yeah, this would it'd be right up that street basically, because I've done loads of tests and stuff, and but I've never really sort of done them from scratch per se. So yeah, I thought that'd be good, but didn't turn out to work out well. So basically, let me shut all these because they're going to distract me. But yeah, I'll get it set up properly. It's just I'm always a last minute when it comes to these things. I just sort of do it. Oh yeah, I'll just do it now, and then I don't actually set things up. Try and set things up, and it all breaks. Okay, so we're on eta reduction. So we did some cool things, and then we did oh no, or did we do contains? I can't remember if we did contains. Let's have a look. Hint. What is this one? Okay, implement a function. No, we haven't done this one, it looks like. We did. Oh, this was like another example of we're playing around, and we're going to put that. I think it is more related to this, so we'll put that there. Yeah, cool. So we're going to go down, smart replicate. So that one, I can quickly talk through it, because then it's like a little mini recap. So the idea was that is you pass it a list of integers, and then it replicates each value the number of times of this. So this, it would repeat three times, and then this, it will just not repeat. Well, it'll repeat itself once, and here it'll do it twice. So you can see the results like 3 3 1 2 2, and then well, I think the hint was like, I don't know, I couldn't do it, which is like a good sign. But it said use map and replicate. But when we were using map, I'm sure there's a way, much like any language. But when we were using map, we were basically getting lists of lists. But we couldn't concat them. And concat, if we have a look, hold on, I can do this. Here we go. So on the right hand side here is the REPL. So in here we can just sort of test our code. So, oh, hold on, let's tell it no. And then we'll load, we're chapter 2, aren't we? Yeah. So if I do load, find it, chapter 2, cool. And then from here, the idea of concat. So concat's like this. So you get a list of lists, and then you can turn it into just a list. Can you see down there? Yeah, I think you can. What was I going to do? 6. Yeah, so basically it's down here. I'll highlight it. Maybe I guess that's, let me look on the left. Yeah, you can see that. I have to sort of peek to the left to see my camera. Is that right? Yeah, it seems right. So there we go. So we had a list of lists, and then we basically concated it, which concatenation, I guess, brings it all into a single list. So that was the problem, is when you use lm, when you use replicate, if you look at its type at the top here, it takes an integer, it takes a value of a, and it returns a list of a. So ideally, if you pass it, say like 3 and true, like the type true, it'd return true 5 times. Yeah, so that was cool, but look, it returns it wrapped in a list. So when we just had issues with inside a map, because once you're inside a map, it expects it to be, because if we look at let's have a look quickly. How can we look at, can we do like that? Hold on, we can do like this. There we go. Cool. So if we look at map, so that expects an array sorry, like a list of A, and then it does a function that does an A to B. So what happens in the map, for every element we convert an A to a B. So you can, so an example of a map working, if I like hard code it, okay, did we explain, I think we explained lambdas as well, didn't we? That was good fun. So if we do like this, so we can do this will only work with integers, okay? And then there's another way of doing this, which is what I think eta reduction will kind of go into, but I'll demonstrate it anyway. So this is an example. Okay, so given that, let's reload. Yep. And then if we call poop, what would you expect the output to be? Okay, well it's just 2, 3, 4. I mean, if it's not obvious, what happens is this value comes in. So it does it one at a time. This comes in, that becomes A, and then it's A plus 1. And then it gets ready to sort of create a new array. And then 2 plus 1 is 3, 3 plus 1 is 4. Okay, so then that's how you get the 2, 3, 4. So you're essentially adding 1 to every single value. But when you run replicate, that doesn't return a single A. It returns an array of A. So then you like try and concat. Yeah, basically you need concat map, and I don't know how you do it with map. So yeah, so map's really cool. You could see, you know, you've got like you're able to iterate over every value and then do something to it. Another trick that you can do is you can see sometimes if you see something here. So this is a lambda. So the idea of a lambda, it's a function expecting a value. We did sort of speak about this, but most of Haskell's are just things, and I think I used a terminology which was terrible, but I'm going to take it. It's like, you know, it's like a Hoover. It's just waiting to suck things up, so like that. And then this A is just awaiting something to arrive, and then a map will do that, and it'll just push it in, and it'll be like, oh, okay, I need that. Do something with it. Then next one, until it gets to the end when there's no more. And also you got to remember is Haskell. This will never actually be mutated. It's going to create a brand new array of integers or list, which is, you know, is cool basically. Yeah, and this is a shortcut that's going to short you. So whenever you sort of see which is part of what's our next one's eta reduction, this is just going to keep complaining until I add a signature. So we'll just do it like that. Cool. And it's basically doing the same, because if we look at the type of +1, whoops, yeah, if you look on the right hand side there, you can do :t, and that gives you the type. And if you see, it's just of the constraint of num. Num is like a class. So another place, actually, in case you don't know, we can go to Google for Haskell, or Google for Haskell. And if we look at the num class, boom. So I'm checking out this here when we've got our type. So our type is num A and A, and you're just like, okay, what do you mean? Oh, and you notice this fat arrow. So that means the A is constrained, or that A is actually part of the class num. And if we look at this num, oh, I've gone down here. Here we go, and we look at all the instances of num. You'll see it's like double, float, int, int8. Do you see what I mean? So any of these, as long as it's any of these, look, all of those, then this this +1 will work on all those, and that's basically what it's saying. But if you, more importantly, if you look at the type, so we'll compare it with just plus on its own. See, that's now it's expecting 2 values and returns us a single value. But when we've partially applied, it's called, so we've just, in Haskell you can do this, you can just set up a function to partially apply its value. So you can just say, okay, well, I'm going to give you like part of the computation, like, you know, I'm going to set you up, I'm going to give you the first A, and now we've created a new function that expects just another value, which, you know, would sort of sit in there. So do you see what I mean? So that's like, how cool is that? You can basically make new functions out of functions that are expecting, you know, so you can alternate what you do to the first values. You can have, you know, this could be like a function called +1, and then you can make another function called +5. But ultimately, you're always using a plus, aren't you? So yeah, it's pretty, it's pretty extensive when you do that. And the REPL's a really nice area. When even it gets a little bit more complicated, the REPL, once you get on bigger programs to try and do things. That's when I start relying on type holes and things like that. But when you're, when we're doing things like this, it's really cool. You can just go, you can check out a type of something, and it'll tell you, and then you can sort of experiment, which is nice. So let's get on to a task, because I end up talking lots and never actually really coding. Which is probably good, because then you get intuition from just constantly hearing me repeat the same messages back home. Implement a function that takes a number, a list of lists, and returns the list with only those lists that contains a passed element. Okay, don't quite get that yet, but let's have a look. So it contains 3. So you've got a list of lists. Okay, I can see that. Oh, okay, and then it looks through a list and it sees if in that list does that contain the number 3. So does that contain number 3? Then yeah, return it. Does that contain number 3? Then return it. Blah blah blah. Yeah, that makes sense, doesn't it? So let's try and do it. First, we want to see what we're going to do. So we'll give it a type, because I think we can work out. So contains. So the type for contains is, well, if we can see, we return. Well, it's a list of, let's say int, and then it will return exactly the same thing. Okay, so we've got that bit worked out. Not when I do that though. Okay, that's cool. And now let's work it out. So we're blatantly mapping over something, but if we look, we're like, it's nested, isn't it? So we're gonna have to somehow I'm not gonna, there is other functions we can use that will sort of go in there, but I'm gonna do it, from a point of view that you might not have ever sort of done anything more advanced. And I don't think we've not looked at things like fold and things like that yet, so I won't do that quite yet. Okay, so we're here and we've got, so let's have our x's. Okay, and then at this point let's use a type hole, and I'm gonna say goodbye on the right. So that's what it wants to return. Let's rotate. No, I mean technically it's telling us something right, is it? Look, it's saying x's is of the type list int. Technically you've got x's in scope, so the valid hole, what you could replace it with is x's. So yeah, technically given the type we could just return x's, but it won't do what we want it to do. So we, first and foremost, we're going to have to map, aren't we? We're going to have to map over the first to get access of these, aren't we? That makes sense, doesn't it? And then if we look at, it says use the, so hold on, let's I'll set it up with a lambda first, and then if we do lm, okay, so if we look at the type there, it takes an ta, I'll explain that in a moment, an a. Aren't you missing the parameter you're checking for? Hey Peter, the parameter I'm checking for. What, the x's on the left? I think that's what you mean. So this. Yeah, let me know. Yeah, there's a bit of a delay, so it's a bit weird, and then you've got to try and type it out. Don't worry, I'll catch it when you write it again. So what was I doing? lm, and then we'll do x's here. If that's what you mean, potentially. So this is not going to work right now. So let me turn this on, if it will. The 3 in the example. You mean these? Oh yeah, of course. Yep. Look at that. Someone knows what they're doing, because it's surely not me. Very good spot. So we'll have This is why it's great doing it like this, because people just point out your damn mistakes. I just spotted it when I... no, I won't call it X, we'll call it A. There, let's call it something... D. Why not? Okay, so this is going to complain straight. Well, for... Let's put a thing in here. Okay, so in at this point, if we look, it expects here to return a list of int. So that's good. And then if we go check out something, so if we go back to Google, and we'll check out the type of LM, okay? Because I was going to explain it a little bit. Yeah, thanks, Peter. I was getting carried away. Good old Google. Hey, Grapher, how's it going? Oh, I've lost it. Where was I? What was I looking for? LM. Find me. There it is. Here's Google. Okay, so it's basically saying it takes a value. So that's a value that it will look for. And it takes a T of A. Oh, you figured it out? 3 monads. Have you? Right, doing well. Sweet. You have to... did you go through like a tutorial or something? Or did you just bang your head against the wall a few times? Yeah, I'll carry... you answer me. I'll carry on with this. Yeah, so it takes a value that it wants to check against. And then you see a T, and then that might be slightly... Oh, it's not showing another type in here. But anyway, a T of A, and then it returns you a bool, so if it's true or not. So the idea being, the T of A would be like our list. Yeah, so for us, it'd be... Let's copy this. Actually, well, I mean, it should have just done... yeah, there we go. Yeah, so you can see the T now. I don't know why that didn't show it up. Let's force that to create a... It'll create a type for us, and then we can use it. So, yeah, the walls are gone now, so guess the answer... That answer... Oh, wicked. Add signature. What's a ambiguous type TO? Yeah, don't worry about it. Shush. Any... Whoa, that's not the one we want, is it? What is it trying to do? It's using the wrong LM. Where's the LM come from? I think it's just base, isn't it? Why is it not giving us... It's not playing ball. Go back. Go forwards. Go to Google. Type in LM. Did I pick the wrong one? Old list. Byte string. No, it is the right one. It's just at the very top. LM. So it's in base. It's in prelude. I don't know why. Why does it want to cast any? Add signature. I've bought in the wrong LM. That's basically it. It thinks it's a different LM. There we go. But that should be the one. But you see, you type it in, so you pick that one, and then it... Let's just reload it. Don't trust it. If not, we can... Oh, let's just go back at the type. I know what it does. Yeah, so that the T would essentially be... The T is part of foldable. And that's just like our list. So the idea being, look through the list. Does this value exist in that list? If it does, true. If it doesn't, false. Okay? So let's... Actually, we'll try and just use it. Yeah, just go away. I don't know why it's doing that. Cool. And then, what was it? Was it O and something else? REPL. I think it's just capital R. Yes. No, don't want it there. Want it in it. O-R. Definitely don't want them. Let's get rid of that. Let's go there. There we go. So we're going to experiment with LM, which should just be in scope. And we'll do 3, and then we'll do it like this. True. You see that? So I did LM, 3, 1, 2, 3, true. Let's try again. And obviously we'll just make it fail now. 3. Whoops. 1, 2, 4. False. Yeah, so we're looking at this. Again, in case you didn't know, these sections is just like some warnings. But if it's, the idea is if it's green, it's good. If it's like some random colours, it's bad. So I'll show you a random colour. Here's a random colour. This is going to break. B. There we go. The colour's bad. Actually, I can quickly explain what's the error, because that's good to start understanding errors. It's saying it can't make an instance for num char. So ideally, if you basically look, you know, when I showed before the num class, and we looked at all the list on the right of instances, and if we went all the way down, it had like int 8, it had double, blah blah blah. Well, there doesn't exist one for char. So basically, the compiler can't match a 4 with the char, which makes sense. Of course, it's not going to be able to do that because 4 isn't a char. So we're one step closer. So what we want, so we know that these, if we look at the A, let's go, hold on, what am I going to do? I'm going to do that. Yeah, it's a bit weird, I don't know why. Okay, cool. So we know that, where's our A? So here we go. So we found a hole, we want a list of ints, and we know to start off with that A, so this value coming in here, is already a list of ints. So that's cool. So lm will just work against that, won't it? X's is a list of ints, and then D is an int. So that's D. So we know from the get-go what we can do is, so if lm, and then we'll use the D, yeah, is A, so that's going to return us a true or false. Okay, so let me just put it, oh, I don't know why, probably don't want it there, but if then, okay, so if it's true, and I'll bring that, wow, I don't know what sort of coding styles I'm using here. Yeah, so if that's true, so if the lm is in there, then just do that. Otherwise, whoops, just return an empty one. Yeah, and then I'll show what happens if you do, well, if they were to all be empty, and then it just literally returning an empty. I'll demonstrate. It's easier to see than, I could have probably just made that on one line. Oh, croaky voice. Okay, so can we see what's going on? So we're grabbing the D, we saw that that's that, and we know that lm expects, its first value has to be an integer, so what we're looking for. The second value is an A, so if you look at the top here, it's a list of ints. So that's exactly, it expected a T of A. So T is the brackets, A is the ints, okay? So list of ints, and that returned us a bool with lm. So if we look at lm there, that's, well, it goes onto a new line, but it returns us a bool. Cool, so we know that obviously an if then is you know, it checks equality to us, it's like a boolean check, so it'll just go, if it's true, then do that. If it's false, then do this. So we're just basically saying, well, if it's A, return A, otherwise, return that. Okay? So let's just test it. There's other ways of doing it, of course there is. But we're just going to try and keep in scope of this, basically. Because otherwise, it goes a bit crazy. I wish there was another way of doing... If I do that, and then I'll go to that window, and then I go to this. I guess that kind of does it. It's a bit. I'm going to do that then. And then what happens if I, from here, or maybe I'll do this. I'm going off now, going way off road. There. No. Oh. Oh, excuse me. Right, stuff it. Just keep going. Okay. Don't know where I was going. So we need to reload. There we go. And that will reload all of our stuff, and then we'll run this function. So it contains what was the value. So we'll test what they gave us to see if that gives us any clues. Except now I'm just get rid of that. Yeah, so we're going to test that, aren't we? Cool, cool. We're going to pop that in here. And is it... Oh, no, I've got it wrong. Okay, so we don't want that, do we? I thought that was just going to combine it. So, how are we going to get around this? We need to not just return... Can you see the difference? Here, it's basically just ignored it, hasn't it? But here, it's returned us, which is my fault, because I returned something here. What is an alternate solution to this? What is an alternate solution? So, oh, but we don't know folds yet, so that's a bit weird. Let's think. How can we do it? That's got me a bit stumped. Or can we just go round? No, we can't, because we have to go at some point. This always happens. So once that... whoa, look at all these different things that can fit in there, which isn't any good. So lem, that's a true. What do we return if it's not found? I guess what we... Oh, I know what we can do. Can we? No, we can't. How do we ignore the... Oh. Okay. Let's have a look. Yeah, so we can do map. There's another one. Memory's gone. I don't want to... See, the thing is I know the answer if we were to use, say, like, I don't know if people know it. I don't know if it's too early to bring things like that, so you see. Whoa. Fold out. Folds. Yeah, we could do something like this, you see. But that's potentially a little bit too early to do things like this. So, let's try and work this out. We can do it. We could do it over... Oh no. I was going to say we could... what would... Filter. Filter! That'd be the one, wouldn't it? Yeah, filter. Of course. Instead of mapping, I can just do filter, can't I? Yeah. And then it's just A to bool. And then R. Yeah, of course. Ugh. Yeah, that'd exactly do it. Look at that, just swap it. Okay, so I'll show. Thank goodness you're here, Gaffer. I'd have gone round and done all sorts of mentalness. I get this, I just get brain freezes on like really simple stuff. It always happens. But what can you do? It's reality. I'm just going to go through filter. So yeah, filter, it basically it keeps things in and throws them out if they're there or not. So you have to give it a function that takes an A to bool, a list, and then so it'll evaluate. So if we look at our A to bool, this is our A to bool, because we know that that's takes an A, and then it returns a bool. Technically, if we wanted, we could do a bit of this. That'd do exactly the same. Because if we remember when I spoke about it, this just gets added. You know, we've basically created a function that expects another function, and because the A is here and on the very last element, you can just get rid of all this stuff. We'll leave it in though for clarity. Oh, and we'll just watch things go weird. Let me just show filter in use. Oh, you know, okay, hold on, I've got to make an error. It seems. Yeah, what's an error? Then it'll show me. Okay. What was I going to do? Oh no, I wasn't going to do that. I was going to do this. Let's just go on to this. Like that. And I'm going to demonstrate filter. So filter. What shall we filter? We'll get a function. Okay. And then we'll do this. 1, 2, 3. Okay. So filter anything that is equal to 3. Oh, sorry. Keep things that are equal to 3. So if we want to do the opposite, it'd be it's that way around, isn't it? Oh, I always forget because they're all different in different bleeding languages. 1, 2, 3. It's definitely not like that. Okay, so filter 3, and we're going to go 1, 2, 3, and it's still not that. Okay, am I doing it totally the wrong way? Is that that? No. Let's find out. Not equal, please. Come on. Why do I get... This is like a brain freeze of almighty brain freezes. Type? No? Okay. Let's give up. I can't believe I get this wrong. Equality. Yeah, find that. Didn't I just do that? I'm sure I just did that. Literally, I did every other variation apart from that. Okay, ignore. How can I remember it? It's like, what? Because I need to remember it. Because let's be honest, it's been 4 years and I get not equal wrong. Something's wrong, isn't it? What does it remind you? I guess it's kind of like, looks like a head of a dog or something. Probably the best way to remember it. So that's like the little bit and that's its mouth. Or yeah, that's it. It's in my head now. I should have just done that 4 years ago. Cool. There we go. So, you know, whatever's not equal to 3, keep. And if it is, then... So it's the opposite way around we've just done. Okay. And if we then look over here, we're basically doing similar. Oh, yeah. Hold on a second. I always miss out the opportunities of... there we go. That's me. The thing is, I don't mind looking stupid. Don't really care. You know, even though I do... Well, when I am employed, I do this full time. And I can happily do, like, way harder stuff. But, I don't know, just sometimes you can't get everything right, can you? And for me today, it was... it was equal, not equal. Just happens. You shouldn't be. I think that's kind of... That's another thing I find, like, baffling, maybe, with... Because, say, like, Haskell or maybe PureScript is seen as, like, a complex sort of mathematical language. No, I meant the bot equals looks like a sad face. Oh. Not. Oh, like a sad face. But I can just see a dog now, so... Actually, except I don't know which way. Oh, like that way. Look at me, like, twisting my head. Oh, it's kind of like a... I'm not sure sort of face. Oh, yeah, okay. Yeah, but then I get confused as to... That's the thing, I get confused. Okay, I understand that this has to go first, now. I'm going to keep with dog. I know sad face is clearly the better thing to go with. But the problem with sad face, and I'll go, well, which side does the smile on? Is it that side? Or is it that side? See, because that's not a very good dog. It's clearly leaning the wrong way. But if I get a good dog, which is none of these, there it is, then, yeah, there it is. That's a good dog. Stuff it. Yeah, so what I was saying is there's a whole perception that you're meant to be this genius. Yeah, dogs, of course it works in my mind. Everything works. That you're meant to be this sort of mathematical genius, and it's you know, once you get it, you're above everyone else in your lovely ivory tower. But it's not reality. You know, I think that maybe especially Haskell, it's kind of like 90% of people struggling Pretending they're not, and 10% that are getting it and are sort of vocal about it. And it makes it look like the rest of us are all meant to be geniuses, but I don't know. Or maybe I've just got this totally wrong, but that's how I feel anyway. So yeah, I hope that by showing that I do like really simple mistakes, yeah, I've worked on massive code bases, is I don't know, it'll just make people feel better, because I get a lot of imposter syndrome, like for sure. You know, I kind of think like, oh man, yeah, oh well, good, as long as you do as well, Peter. Yeah, see, there we go, we're at 90%. That's what I mean. It's like, I don't know, it's really easy to get imposter syndrome, especially say you look on the Slack channel of the main Haskell bit. You're just kind of like, whoa, what are they talking about? Even now, I mean, I understand a lot more now, but still, it's I guess it's like intimidating is probably the word, so it can be. So, you know, oh, biscuits. Oh, what do you mean, though? So my wife's just, I've eaten all of them. I'm not allowed any more biscuits. Oh, damn. Yeah, so I don't know. I think that I wish that this whole persona of maybe it's not just in Haskell, right? It's potentially also in the whole of development world, but a little bit more so in Haskell because of its academia background and how it's so connected, you know, to being, yeah, we're all, I don't know, I wouldn't like to say everyone feels like they're geniuses, but there is that air of that, and I just want to demystify that, because, yeah, you know, I'm by no means a PhD guy with any sort of thing, so don't feel dumb. Just keep going like me and bang that head against that wall until it makes sense. And the thing is once you get deep enough, which doesn't take long, once you get to like, I don't know, you know, probably once you're able to do this and you see it in, you'll start getting hooked and you'll be like, ah, these types and this, you know, being able to do this. I mean, there's not many other languages that can do that for you. And that's all because of, you know, the types, because you're pre-setting up. I guess things that there is obviously there's other type languages and there's, you know, pure script and things like that, but it's strictly type languages. Is, you know, a lot of other languages have gotten around it by making things a little bit looser, and I guess like JavaScript, TypeScript kind of tried to go that way, but it's still not as extensive as this. Do you know what I mean? These are like simple functions, but you'll see as we go on, you can really be thorough with your types and do all sorts of, you end up basically your types, you can make functions out of types. This is when like things start going out there. Anyway, let's go, stop talking. So heteroreduction, another sequence of the Hoff. Where's the Hoff? Hold on a second. Hoff, if you don't know what Hoff is, I'm gonna just show you quickly. Here we go. Where is it? Did I go to that one? Yeah, I go to that one. Where's our Hoff? We did this the last stream as well. Here we go. Higher order functions, aka Hoff. The Hoffman. There he is. Looking sublime, as always. Not when he's eating burgers. Ooh. Yeah, so that's a higher order function. So the higher order function, we kind of showed some examples of that. Yeah. Where we were sort of splitting things up. Well, basically, you're able to pass a map. So that's the ability to pass a function to another function. Yeah. So the map expects a function. So you're able to, like, not only can you pass values to functions in Haskell, you can also pass functions to functions. Which is cool. And so another consequence of Hoff and partial application. Partial application was this, you know, when we just added plus 1, that's a partial application because it's awaiting another value. Okay. Is heteroreduction. This term is used to call the simplification of functions over their arguments. Specifically, if we use foo x equals bar 10x, yeah, this precisely means that foo is a partially applied bar 10. Yeah. So we did it with, I just showed various examples that do that. Actually, if we just put this in a line, then it will probably be a little bit clearer. Cool, you see. So, and then if we imagine that bar takes another 2 values, bar 10 does, sorry. Or, sorry, it takes a single value. Oh, yeah. Oh, hold on. Surely there's a gap there. Let's imagine there's a gap. Yeah, so we're partially applying bar 10 with 10, and then we're waiting for this value to come from here and to go into the bar. So this is always going to do. So we can imagine that this actually just times it by 10, and then we're going to pass whatever number it is into there. Okay. The foo is partially applied for bar blah 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 blah. Okay. This concept can be used to write functions as well. For example, so the next integer is, so in this scenario we're just trying to, you can see, literally add 1. So we're partially applying the 1 to add. Okay. And if we know, if we just go, how am I going to open it? I wish I could open it in a new window. Okay, it doesn't matter. What was I going to use? I forgot now. I was going to use add. Yeah. Oh, see, this is a problem. Anyway, so add just adds a number. So add 1, 2, and equal 3. Okay, in this scenario, we're saying add 1, which would be the next. So we've created this function that is partially applied to 1. So it's always going to be add and 1. But then we're saying that the second value is actually going to come from here. So this will just wait, you know, it'll give it the old Hoover job, waiting. And then as soon as we call this with that value, it'll go, oh, okay, I've got my second value now. I'm going to return you the result. Okay, but in this scenario right here, it'll hang out. It'll just, you know, be out there with Hoff on the Berlin Wall, you know, singing tunes like he did when the Berlin Wall came down. Because, you know, he's the Hoff. Though this is not quite, well, it's a little bit related, isn't it? It says it up here, Hoff. Okay, so does that make sense? I think it makes sense. So we've got the ability to just, you know, build these up. And now you could be written in a eta reduction. So much like I said, if you see, look, if this on the left hand side, so imagine, let's imagine, I'll go through this example and then I'll expand. So we've got an n, and then if we see that's the very last value. So if we didn't, so this, okay, like I did show, I don't know if I showed in this one, oh. But doing it like that, whoops, here we go, is exactly the same as doing that. Okay, so we've done a lambda which expects an a, and then we're going to pop that a in there. And then, you know, but you can literally, so the idea being, if there's an a here and on the outside, so the very last value, so you can see it like this, it's like, I've got this, I know I'm waiting another value and I'm going to use an a, but if it's from here, it'll automatically pump it in. So you know that there's a value waiting to come in, and this, you know, you don't need to repeat yourself basically. Haskell allows you not to have to do that. And that's called eta reduction. And much like, you can also do this. Like that. Whoops. So we can do this. Let's do that. And then we can do that. And if you think about it, in that scenario, technically there would be an A and a B. And then it would just go in that order. A, B. Yeah? So it's pretty cool, isn't it? But you can't do it like this. This would throw an error. Let's have a quick look at that error. Let's have a look at that error. Error. It's my favourite. I've gone the wrong way. Look at that. Still not fixed it. Sorry. Cool. So look, there's an error. It's saying variable. Well, first and foremost, it's not in scope. So that's good. Hold on, let's just create that. So I guess, hold on, I'm going to do this first, and then we're going to do this, and then we're going to just create a function that just does it. There we go. Okay, so we've created that function now. Cool, so that would work. And B. Now it doesn't work. So if we look at the type error, it says couldn't match the expected type int. So it might not be like too clear as to what's happening. So if we look at here, look, so it's just saying couldn't match the type int with the actual type int. So what it's, oh, it does say, look, too few. Why isn't that coming up? Come on. Let's make this bigger then. Add is applied to too few arguments. So look at that. So it's basically saying, well, you've not given me, I expect this function to literally just return an int. And that right now, you've just given me an add. And if you look at it, add is just int. Oh, sorry, it's actually literally underneath. So you've not given me any values to it. So I can't return you an int because it's missing values. So because you do that, but once you remove those, that's then it will automatically add them on. So really, that's like, I think that bit me not even that long ago with something else. And I was just like, why? What the hell? Why is it not reducing? It's like, you've left the value on the left. It's not going to work. Especially when you do that. And it just goes all the way up to the top. There we go. Yeah, so if you leave that value, not happy. Let's go down a little bit. But if you remove them, auto currying. Boom! And that's what the act of that is currying. If you've heard the term, that's what it is. But it's part of eta reducing. So that shows you that example for us. Next int, yeah, so you can see we've just partially applied, and then whatever would be there goes straight onto it. So note, see, the initial type of the function is not changed and it works absolutely the same. We just can skip the last argument and amend its usage in the body of the function. Yeah, just remember to take it away from the left if you've declared it on the left. So if you haven't, you'll get that error. And yeah, like I said, it bit me, but it was like nothing like this. It was like something way out there, and I was just like, what is going? Oh, okay. Yeah, so literally. So I mean, is this asking us? Now let's try and eta reduce some functions, ensure that we can master the skill of eta reducing. Okay, well we can see here clearly there's an x on the left, and the last value to go in is an x. So let Haskell deal with it. Thank you. Cool. To do the type. Oh, okay. Well, we won't cheat because this clearly shows us what the type is here. So we'll look away. Let's do list elements than. Let's have a look. So it's a filter x1. So I guess x and l, isn't it? So x is going to be an int, I'd assume, because filter less than. So less than we know works over num. Actually, we can keep it like quite. Should we concrete it? Yeah, why not? So num a, and then this fat arrow. So if you see this at the function like we did earlier on today, that's a constraint. It's saying that the a is going to be of the class num, and then when we looked at the class num, we've got things like int a, double, etc., etc. So we're saying all the a's in this type signature are going to be of the class num. That's why we're constraining it to. So x, it looks like, is just going to be a single int. And then we know that filter, so if we look at the type of filter, that works over an array there. So an array of a. Or a list, sorry. So we're going to have a list. Hello. Keeps doing that. Of a. And then what's it going to return? What does filter return? So then we just look at what filter returns. Filter returns a list of a. So then we have another list of a. There we go. Except I got it wrong. So it's not happy. Oh, it's odd. Okay, sorry. There we go. Again, it's a different class, but the class of odd, because if we look at this, let's have a look. I'll show you why. I will. Oh, well, you can see in the type there. Oh, Hoffman. If we look at the type, for all a, odd a. So the class isn't num, it's odd. And then if an a and an a, and it returns as a bool. So you know it's less than. So you have to, because they're different. Num and odd. Odd is a type class that deals with ordering of things. It doesn't just here. This is another cool thing. Watch this. So if we go into we'll go into here. Are you going to open? No. Why don't you just... Okay, just fail, then open. 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 No, there it is. It's open. No. Okay. Well, let's go like this. Ord. So, type of ord. Oh, sorry. What am I doing? Okay. Less than 5. False. Okay, so we're using it here. 10 is less than 5. Remember? Yeah, this is why I actually wanted to. So we're looking at a type. So it's ord AA. But the A is still like the word that we used before is polymorphic. Okay, so it's still like saying, okay, well, it's an A. As long as it's part of ord, then I'm cool. Now guess what else would be a part of ord? So if we do A is less than B. True. There we go. So just have a look. We'll veer away from Hoffman. And we'll go to Hugel. We'll go look at ord. Class ord. There we go. And if we look at the instance, so we've got the class ord, okay, and then to see what's in part of it, we'll go down in instances. So it'd be like a bool, a char, a double, a float, an int a, blah 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 blah, and the list goes on. See? So it's, you know, it's not like what you can do. Oh, this is another trick. I think you can do. I can't remember if it's that way. No, it's not that way. Was it the other way around? Or was it B? I think you can like, I think it was maybe B. I can't remember. I've forgotten already. No. I thought it was something like that. So basically you can imply what it's going to use. Maybe it's like at int. Int, especially when you do the right at and the right letters. No, that's going to be wrong as well. So what the hell are you talking about? Okay, I've forgotten. I was going to try and make those types concrete. But actually, what am I doing? I could just do it like this, couldn't I? To show the concrete typing. We can just look at the type of this. No, that's not right either. Oh, I've got another answer. We can look at the type of... Except I've gone the wrong way. Let's do this. Oh, I forgot how to do the constraint. You know, like to... Cool, okay. Well, we know one of the values is char. So that constrains it to char. But never mind. I should... no, actually, I'm going to look. Why not? There it is. It's all somewhere in there. I thought it was B. I thought you could pass it B. But it's not the letter B. Sorry, I'm just moving away from the mic then. Let me look. Is it plus? Plus. No, it can't be plus. Allow multiple line commands. No. It's not. It's not set. Run. Type. Which is, well, basically every time we type T, it's basically type. Oh, plus D. It's D, not B. Shows the expression default into type variables. Okay, so that's cool. That's what we want. But I'm looking if there's... let's just use this one, shall we? For now. And then there is another way to sort of... except I've just... Yeah, don't worry about it. Just do that. What are we doing? This... Let's have a look. Oh, damn you. That's not helped at all. There's a way of doing it to constrain it. But basically, minus all that. That's what's going on there. Let's go back to this quickly. Okay, so we know... So from filter, have we... No, we haven't fully reduced this, have we? So if we look... So let's try and add to reduce. So we know we can take this one away. That's for sure. And we know we can take that one away. Let's save it. Okay, it's happy there. Do you reckon we'll get away with the X? Let's try it. No, we won't. Only so far. Yeah, because at that point, filter is expecting a value to come in. and the second function of filter. So you've got a second function of filter is a function of a to bool, which is exactly what this is. Well, it's not. It's actually it's an a. Yeah, it's an a to bool. No, it's not even a to bool. It's just, oh yeah, it is a to bool. But we can't just randomly, you know, at this point here we've reduced filter for it to expect that part to come in, which is fine. But then the next part is this. But then we can't just throw that in there by some sort of miracle. Was it that way around? Can't remember which way around I went. Yeah, it was that way around. So yeah, you can only reduce it that far on this one. Then, can you reduce this one? Let's try it. Actually, let's give it a type. Oh, where am I going? Oh, gone the wrong way. Oh, just go to the beginning, please. CA, and then we'll add the signature. Why not? Let's have a look. Zip width. What do you reckon? Let's have a look. I'm going to delete them all. Bam. You sure can. Because if we look, you see that? It's literally, it's going to take it in order. So the first one, that'll go into there. The second one, that'll be the next in line. So you can keep going. But obviously you have to have a function, even though it's showing you zip width, which we've not used at all. But if you look, the function expects a function of A, B, and returns a C, a list of A, and a list of B. So we know that if we look, that's our list of, they've called C here, but you know, it's just, oh, and another thing, if types, you know, if here it's like name C, it's when they're lowercase, it really doesn't matter, especially when that's gone wrong. It really doesn't matter what they are. You know, all we're looking for is they match. So then when you look at error messages, so if we just do a bit of this, because something's gone a bit funky here. There we go. So if we look, what was I saying? Totally forgotten. Yes. Why is this not happy? X is not in scope. Of course it's not in scope. There we go. It's in scope now. Whew, calm down. Yeah. So here, so if we look the C, and then when we look in, let's look at the error messages. So if we look on the right hand side, variable scope Y is not in place. Okay, so that's like, oh, I don't know what you're talking about. But if we look at like zip width, let's have a look at the types. So you see it's like A, B, C. Why does it not match these C's over here? Well, they're irrelevant. Don't think of them as like that they have to match. Only things that have to match is when they're like this in uppercase, when they're an actual type. These are just saying that, by the way, we're going to constrain this. You know, look, I could literally make that whatever I wanted, but we've got to make sure that they're all in this scenario anyway, that they're all the same. Okay. That worked fine. It's not a problem. And then if we look at zip width, it will do the same thing. I mean, this is getting it from the docs. It's gonna. So yeah, zip width takes a function that expects two values, and then it grabs a list of a value of A and a list of value of B. So if you look, it's clearly taking the A's and then the B's, doing something, and then returning C's, and then packing it all back in a list. So it's like a, you can think of a zip. Zip comes from like the idea is like a zip of your jacket, and then if you think about the actual zip, it's got teeth, hasn't it? So it's got like teeth to go like this, like this, like this. There we go. And as they come together, boop, 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 they create a new list. So that's basically what it's doing. I won't show it yet, but that's the idea. Yeah, and in this scenario, we know that that's a list of whatever, which is of constraint num. They're there, and this is the first value, so we can literally just rip it all out. We're going to go, no, don't even need to mention all that, because it'll automatically suck them in, especially when you do this. Sweet. Okay, lazy evaluation. I've basically gone over this, but let's do it again. Another unique Haskell feature is lazy evaluation. Haskell is lazy by default, which means that it doesn't evaluate expressions when not needed. The lazy evaluation has many benefits. Avoid doing redundant work. Provide more composable interfaces. When we say composable, what we were talking about last time is Legos. So composable is like, you know, when we were just talking then about having functions that expects other functions and bits and pieces, you know, you can just literally, Haskell is like a bunch of Legos, and the idea is as long as you get an input, you're going to get the same output. Okay, so whatever same input, you'll get the same output. So for example, if it's a +1, it sits inside our little Lego brick, but whatever input you're going to do, it's always going to return +1. It can't do anything else. It can't like do things like that. But we can then use composition, where we can just use that little piece, and what we're doing, like the partial application, what the +1 already is a partial application to add. But do you see what I mean? So we're able to just build up all these different computations using little pieces. So you start thinking about problems in a slightly different way. You start thinking, okay, well, I can make this function, and actually this function can also do something else with another function. So let's change it so it can accept, you know, values, and then I'll deter what it can do given a specific value, for example. Really cool. Okay, so that's the instance of that. Doing redundant work. Here we go. Right, so where were we? The lazy evaluation has many benefits. Avoids redundant, provide more composable interfaces. And in this section, we will focus on Haskell's ability to create infinite data structures and work with them. So what does that mean? So let's go a little bit further. For instance, the Haskell standard library has repeat, a function that returns an infinite list created from a given element. Of course, we can't print an infinite list to our terminal, because if we try, it'll crash our terminal. So, like anything, it will take an infinite amount of time. Yeah, I mean, we could start now, wait, and then, you know, I'll get back to you. But when it'll be in a post. But we can work with parts of it due to lazy evaluation. So let's see an example. I think I've already touched upon lazy evaluation. You know, it's like the whole Hoover concept. Things are just waiting, and they won't happen until they're needed. So take 5, repeat 0. So let's have a look at some business. I wish I could. Okay, let's just go. So let's have a look at the type of repeat. Can I find it? Yeah, so it takes an A and returns. So let's repeat. Oh, what's going to happen here? No, don't do it. Oh my god. What have I done? Got suckered into it. No. Quick, delete, kill session. Okay. I was just talking about not doing it, and I just literally did it. What an idiot. So as you saw, I did repeat 3, and it just went. It just kept repeating 3 infinitely. It just kept going. Okay, because we're just telling. But. Hold on, I've got to find different. No, don't do that, please. God, I sound so English, didn't I? Don't do that, please, sir. Where am I going to go? I think it's that one. There we go. That's where I wanted it, on the right. And now it's done it. Except I've got to load everything because I killed it all. So, no, just leave it. I'm happy with it. This is just giving me tips. Should I delete unused imports? I should say yeah, but I'm not going to. Load chapter 2. Oh, hello. Chapter 1, chapter 2. Hey, thanks for following, Mr. Blade Brown Jr. I like that. It's a good name. Mr. Blade Brown Jr. Sweet. Thanks for joining. What is it? Following. That's the one, isn't it? Yeah. Yeah, I don't know. Twitch. Woo. Like, I don't understand all the Twitch emojis either. All that stuff. Hold on. But I can make GIFs. Oh, did we get... Oh, I missed a GIF. What was it? Oh, I forgot which one I set. I guess you would have seen it across the screen, wouldn't you? It wasn't this one. I've got to remind myself what it was now. I'm going to replay the action. Is it in Stream, isn't it? Streamlabs. I'm going to look for it. All widgets. No, alert box is the alert. And then global events. I think it's when someone follows. What was it? Yeah, it's the skateboarder with a cape on. Whoop, whoop, whoop. Yeah, I do skateboard. So there is a slight connection. Not with a cape. Yet. Okay, what was I doing? Totally lost it. Yes, take. Okay, so if... well, we didn't quite see it, but... so look at the type of repeat. That's what we need to look at first. Yeah, we did do that. And then I bloody used it, didn't I? Right, type of repeat. Look, A to list of A. Okay. What's the type of take? That takes an integer, a list of A, and then it returns us. We did use it earlier on. We used it in some past things. So we can take 3 of 1, 2, 3, 4, 5, 6, 5, 5. Whoa, hello. It's gone to the top. Okay, so and it will take the first 3. So to prove that Haskell is lazy evaluation, so you see when I ran repeat 5 on its own, what a nutter. So if you take 5, I'm going to do repeat 3 somehow. Repeat 3, you'd think it'd blow up, but no, it won't. Thank you, Haskell's got your back. So what's happening is the function take 5, as we clearly see, it'll take X amount of values from a list. So we're saying take the first 5 values, repeat or keep repeating those. And in this scenario, it won't evaluate until take 5 says, oh, I want 5, and repeat, and then it'll just it'll call the repeat 5 times, and it'll just stop it. So repeat isn't like sitting in the background continuously going freeze like you saw. It's literally just going fiddling its thumbs, you know. Oh, like this, sorry. Like that. Until it gets to a point it's like, okay, right, well, oh shit, what's the time? 17. What time did I say I'd stop? I forgot. 6. Hold on, because my wife has got a course, a design course later. It's like an online one, and I'd said, I think in a minute. Okay, I'm going to keep going until probably the end of this. So yeah, so repeat isn't, it's just sitting around twiddling its thumb going, hey, you know, what am I doing? And then take comes along, goes 5, and then it goes, whoa, 5, and then as soon as it gets to the end, take just goes, bam, punches it. It doesn't punch it, that's like quite harsh, isn't it? It squeezes it. For some reason, it's like, squeeze it and goes, oh, okay, I just want 5. Stop, repeat, and then it stops. And then it's not, that's why you don't get this recursive. And that's because Haskell's lazy. Literally, that's all it is. And if you like that terminology, use it. I like to sort of turn things, because I had a hard time sort of learning from books and things like that. Not because I don't necessarily understand them, but I just like to sort of, I don't know, imagine scenarios and images. Because basically the point is if you read things about like memory, and like the memory palace is another example. The mind is really good at remembering crazy scenarios, or like that. Like I just said, you know, you imagine that repeat sitting there twiddling its thumbs, and then take comes along and goes, hey, I want 5. See, that whole thing, you end up visualizing it in your head, and that's going to stick in way more than just reading this sentence or this paragraph. Technically, not for everyone, but theoretically, that's what you know, people that have got really great memories, they use that basis. So they'll put like a shopping list. They'll put a shopping list and they'll put it into like a well-known. So for me, it'd be like walking through my front door, going into my living room, going into my kitchen, and going upstairs. And at each little stage, it will like put a real strong visual. So, you know, we could have repeat that sat there, you know, just twiddling his thumbs and just like at my gate, and then take comes along and squeezes it in 5 times. Yeah, and then you'd remember it. Hopefully. And this does the same. So look, when I'm not going to call that, but that's similar to repeat, except it will go from 0 to infinity. In this scenario, we're just saying, well, take 4 of these, 0 to infinity, and just return me them. So it will literally just go 0, 1, 2, 3. Another example is, you could start it at 10. Yeah, and that'll do that. Oh, another trick, because we're playing along now, we can do 10, 10, 10, 10, 10. Oh no, it's just done 10, 10, 10. I thought it... Oh, okay, it only works if... Yeah, okay, it won't work. You can do this though. 10. No, I've done 10, 10. I should have done this. Let's have a look. This should work. Yeah, it did work. So take 4, look, it'll go up in increments of 10 because my second value is what I want to increment by. And then if we do like this, no, we'll just keep going. 10. Boom. 10, 20, 30, 40, 50, 60, 100. Handy, eh? How cool is that? You've basically, and this is not, and this only happens when you call it. So all of this is just sitting there, waiting, twiddling, being lazy. Isn't this awesome? Yeah, I think it is. It's pretty good. That's like, you can't do that in other languages that aren't lazy. Think about try and think about representing that ability, to create a function that's going to do something for infinity, and then have the power to just take the amount that you want of the infinity. Sounds like some sort of comic book, doesn't it? Infinity. Right, no, infinite lists bring great power. With great power comes great responsibility. I don't run it in your terminal like I did, because that's not very responsible and it'll crash. Functions like length hang when called on infinite lists. Yeah, well, of course, because, the idea of length, well, in case you don't know, it literally, especially when you don't do it right, yeah, do a value this time. There we go. It just counts the number of elements inside the list. So in this case it's 5. But if you were to do that, which I'm not going to do, you do that to, say, what we were doing before, a repeat. Well, no, if we do it to that one, it'll crash. It'll just go, no, got to the end, because I can't ever, length will only return a value once it gets to the end of the list. But if you don't give it an end of the list, then it'll just keep going, and then it'll Stack Overflow, because you're just continuously putting more and more and more and using more memory, and then the computer goes, use all my memory. Can you start off now? Yeah. So make sure you think about such corner cases in the implementation of your functions if you expect them to work out an infinite list. Another scenario of things like that happening is, when we were doing case or pattern matching and things like that, and then we're doing recursion, and so we could calling a function from within the function. So we had like a go. You know what? Instead of like just waving my hands, I could probably just show you some code. Here we go. This kind of code. So the idea here was, I explained it at the very beginning, it's return even or odds. So not by the number, but this would be like odd, even, odd, like that. Okay, so if you can see here, we've got a function called go, and go, we declare it in a where clause, which is basically saying that we've got a function that's only available within the scope of this. Okay, so you can see we call it here, we pass it a b, which is a bool, and then a list of ints. Okay, so if we look at it, and then we do various whatever we do, so we look and then we recall false on it. Okay, but if we didn't have this here, then there's no get out clause. We're not telling this function that's continuously going around upon itself, because that's how we do. It's called recursion. It's much like creating an infinite list. It won't know when to come out. So that's one of the scenarios where it'd bite you right there. Make sure you have that get out clause. I need to stop looping. I need to get out. That's basically what happens. So yep, I'm getting out. Oh look, we're nearly sort of done. Whoa, my goodness. Infinite, yep. Task 11, rotate a list by a single element is the process of moving the list first element of the list to the end. Oh, implement a function to rotate a given finite. So as in like a list with an end by n elements. Try to do it in a more efficiently. Oh, I'm not going to have time to do this, I don't think. yeah, I'm going to have to stop. But that would be a good one to go on to. Yeah, so the idea being, look, so if you look, we're saying rotate by 1, and basically it's going to put the 1 at the end and then shift it all along. So the 1 goes at the end by 1, and then I guess if you do 3, so it'd grab 1, 2, 3, so it'd be like a 1 there, 2, 3, and then 4 would be at the beginning. So there you go, 4, 1, 2, 3. Okay. Use cycle. Oh, we could have done it without cycle, I reckon. But let's look what cycle is. I'm tempted now, but I've really got to stop. That was the deal. I must stop. Cycle. Does it give you an example? Come on, cycle. No. Cycle ties a finite list into a circular one, or equivalently, the infinite repetition of the original list. See, this is where I kind of wish Haskell had examples. Just show me an example, the input and the output. But yeah, that's probably on me. I should add more documentation like this. See, that's got some nice examples. You could like, oh, okay, yeah, cool. And I'm sure I could read that and it'd make sense. But yeah, not to me. Right, I'm gonna have to stop. That's that for today, I reckon. Yeah. So what we'll do is we'll either the next one I'll continue. Either I'll build this up and then we can look at a property-based testing, which uses like libraries like HSpec, or I'll carry on and do this. Because I guess we're only on chapter 2, and I've done like this is a 6th episode, and they're like sort of an hour to 2 hours each, so being pretty damn thorough. Oh yeah, maybe I should do that. I'll link it before I go. Where is it? Your videos. And then that's not right. I need to sort of your channel. Look at my long way around things. My videos. Look at this. Internet famous. 434 people on YouTube. I'm always counting them, obviously. Yeah, that one. So if you want to see the past ones, and then this one I'll put it on when I can be bothered, which is usually like a couple of days later. Yeah, so that's it. So, oh, I've got playlists. If you click on playlist, look. So I've done one for like Journey to Monad Transformers. That's cool. We finished that one now. This one is what I keep adding to. So learning Haskell. And then these are like older ones where I did learning Haskell for dummies, but I didn't finish it. I kind of stopped. And then this one was learning PureScript, which is probably going to be a bit outdated now, because if we look at when they were created, it was a long time. I've even watched my own videos. Can you believe it? No? Got to make sure they're right once they're up. Trying to get that count up, you know. So just going around watching it again. Cool. Okay. Well, oh, the music's just stopped as well. That's probably good timing. I know it started again. Anyway, I'm going to lower this thing. But yeah, well, thanks everyone for joining. Yeah, I think it'll probably be Thursday. I think I'm not going to do anything tomorrow. We'll see. I don't know. It's just last minute. I'll just put it up on Slack or what's the other one? Twitter, and then that's usually the way. But thanks everyone for coming, and yeah, hopefully see you soon. Take care. Oh, I've got an outro. Get ready for this. No, I've got to put the right one on. Here we go. Boom.